Welcome back to the last part of the lecture, okay, which is on the vapor compression cycle. So previously we have learned how to draw a vapor compression cycle onto a pH diagram. Okay, but of course that's not the end, because from the pH diagram we are able to get very useful information, which includes the following, such as the cooling capacity, the amount of energy you need to put in, and the amount of heat that will be rejected at the condenser side, and of course the most important part is how efficient is the system. So first, let's look at the cooling capacity. So the formula, right, okay, generally the formula is Q is equal to m dot delta H. This is the general formula that we are going to use for the next few formulas, next few equations. So of course, for different Q, there will be different sets of delta H. So let's say, before I go into that, let's look at this m dot. What is m with a dot on top? Okay, as we know, m usually is representing mass, which is in terms of kilograms. Okay, so that is representing mass. But with a dot on top, it means the rate of mass. Okay, so when we means the rate means is per second. Okay, so in other words, it's actually the mass flow rate of the refrigerant in kilograms per second. So that's mass flow rate of refrigerant. How about Q and delta H? Q, as we know, is the amount of heat. Okay, the amount of heat either rejected or absorbed, and delta H is the change in enthalpy. So if we are looking at cooling capacity, your Q, right, okay, we will write a subscript Q evap, okay, is equal to same thing, m dot delta H, but the delta H is between 0.1 and 0.4. Why? If you look at the pH diagram, the cooling takes place when your refrigerant is moving from 0.4 towards 0.1. Okay, remember that is the part where refrigerant absorbs energy from the room at the evaporator side. So between 0.4 and 0.1, what is the gain in enthalpy? Okay, so that is your delta H. So in short, you can write m dot H1 minus H4. So that is the equation to calculate the amount of cooling that you can provide in this cycle. Okay, so using the same concept, if you want to find what is the compressor work, that means how much energy or how much power you need to provide in order for this whole refrigerant cycle to work. Okay, it is same thing, m dot delta H, but instead of writing Q, you can write work done by compressor. W with a small subscript COMP to represent work done by compressor is equal to m dot, which is the same refrigerant mass flow rate, multiplied by H2 minus H1. Why is that so? Because your refrigerant, when it's moving from 0.1 to 0.2, it is actually undergoing compression. So from 0.1 and 0.2 is undergoing compression. We want to find out what is the change in enthalpy, and from the change in enthalpy multiplied by the mass flow rate, you are able to get work done by compressor. Lastly, as you can guess now, if we want to find what is the heat rejection at the condenser area, Qcon, heat rejection at the condenser area, same thing, m dot delta H, but now it's between which 2 points? It will be between 0.2 and 0.3. So you may think, oh, I should take H3 minus H2 because it's always final minus initial. But don't worry too much about that. Okay, just take the bigger value, which is H2, minus the smaller value, which is H3. Okay, so in the end, you will still get a positive answer because you have already clearly said that it is a heat rejection from the condenser. Okay, so you don't have to write H3 minus H2 and get a negative answer. Okay, so if you use this formula, you will get a positive answer. So if you notice, okay, these three, right, these three terms, first term, second term, and third term, they are actually related. Okay, they are related. So that is to say, if you look at the pH diagram clearly, you will notice that the amount of heat, okay, that you absorb at the evaporator, Q evap, which is the bottom line over here. Okay, this is Q evap, plus the amount of work done at the compressor, which is between 1 and 2, that means is over here. You will notice that this whole line is in fact same as this point between 2 and 3. Okay, it's the equal length. Okay, between 2 and 3 is equal to between 4 and 1 plus 1 to 2. So if we're going to write this into a formula, okay, it will look something like this. The amount of heat rejected at the condenser is equal to amount of heat you absorb at the evaporator plus the work done by compressor. So you may find this very familiar. Okay, we've seen this somewhere, and it's actually on your slide 32. Okay, so slide 32 is your first law of thermodynamics. Okay, so okay, sorry, it's not on your slide 32. Okay, it is on your slide 21. Okay, if you look at slide 21, okay, so this one is not slide 32, it's slide 21. Sorry for the typo error. So if you refer to slide 21, which is on the first law, okay, using first law, it actually obey the first law. Okay, it actually follows the first law, and it's consistent. Okay, consistent with the law of thermodynamics. Okay, so this is also what we call the heat balance equation. So take note of this equation. Okay. So one thing you have to take note is the units. So what is the units of Q evap, WCOM, and Q condenser? So if you're going to break this down, right, let's look at Q evap. So Q evap is actually equal to m dot delta H. The units for mass flow rate is actually kilogram per second. And for specific enthalpy, the units is kilojoules per kilogram. So with that, if you cancel off the kilogram, you will be left with kilojoules per second. And kilojoules per second is in fact energy divided by time. And this one, right, will give you the units of kilowatts. So for your answer, always write your final answer in terms of kilowatts. So be it Q evap, WCOM, or Q condenser, is all in terms of kilowatts. Okay, now let's try some example. Okay, remember in example 1.2.3, you have already write down the enthalpy value, the 3 enthalpy value. So with those enthalpy value, right, you are able to calculate A, B, and C, which is the cooling capacity, compressor work, and heat rejection at the condenser. So similarly, you may want to pause the video and try it out yourself. Okay, if not, I will continue, okay, and show you the answer. So first, cooling capacity. So cooling capacity is actually equal to m dot, if you refer back to the formula, is H1 minus H4. So refer to your example 1.2.3, what is your H1, what is your H4, and sub in all the values. So m dot is actually 0.2, H1 is 275, and H4 is 105. So with that, you calculate, you will get 34, and remember the units, kilowatts. Okay, so of course, when you draw the pH diagram and you read off your enthalpy value, which is slightly different, maybe 280 over here at 110, your answer may differ slightly, but don't worry, okay? So as long as it's within the range, it's still correct. Okay, so let's continue with part B. Part B, compressor work, as we know, the formula is m dot H2 minus H1. So similarly, sub in the correct enthalpy value, you will get the answer, 6 kilowatts. So how about the last part? Okay, part C. So part C, they are asking for Q condenser. Okay, Q condenser. So actually, the most straightforward way, of course, is just follow the formula again. M dot H2 minus H3. So you can, of course, sub in the value and get the answer again. But there's actually another method. Okay, let's say you don't want to use this method, use this formula. Okay, how can you find the amount of heat rejection at the condenser side? You can do that because of this equation. Remember the heat balance equation. Q condenser is Q evap plus work done by compressor. And you have in fact find these two values in A and B. So Q evap is 34. Work done by compressor is 6. So if you add this up, you will still get the same answer, 40 kilowatts. So you can use either methods to get the Q condenser. Okay, so let's go to the next part, which is the last part of the calculation that you need to know. That is on COP. So what is COP? Okay, COP actually represents coefficient of performance. In other words, it's telling you how efficient is your system. Okay, so COP, the formula for COP is the amount of cooling that you can provide, Q evap, divided by the amount of power, okay, that you put into the system. Okay, the amount of power consumed by the compressor. That's why it's power input. Okay, you can write W in or P in. Okay, power input by the compressor. So take note that this power input is not equal to work done by compressor. Okay, although they look very similar. Okay, because the amount of power you give to a compressor, it is not 100% efficient. There will be some losses, okay, be it electrical losses, mechanical losses, and therefore there is a so-called overall efficiency of the compressor. So they are related. Okay, these two terms are related. The power input is actually equal to work done by compressor divided by the efficiency. Okay, or in another words, work done by compressor, the useful work done by compressor is equal to the amount of power you give in multiplied by the efficiency in terms of percentage. Maybe 90% you will multiply 0.9, 80% you will multiply 0.8. Okay, so for example, you have a compressor and you give a power input of 20 kilowatts. Okay, so this is your power input is equal to 20 kilowatts. Let's say your compressor efficiency is 80%. What will be the useful work done? Very easy to find. You will just take 20 kilowatts, multiply by 80%, your useful work done, it will be equal to 16 kilowatts. So the power input is always higher because there are some losses over here as shown in the diagram, okay, all the electrical, mechanical losses, etc. So with that, let's continue with the next example, 1.2.5. So for the aircon system in example 1. I think it's not 1.5, it should be 1.4, 1.2.4. So again, there's a small typo error over here. So please change the example value. Okay, it should be example 1.2.4. Calculate the COP if the overall efficiency of the compressor is 70%. So how do you do that? So first, to find COP, as we know, the formula is equal to Q evap over power input. Okay, so we have the Q evap value, no problem. Okay, because Q evap is equal to 34. Okay, 34. Okay, But the problem is we don't have the power input value. Okay, so what is the power input value? Remember, it's related to work done by compressor. So W in is in fact equal to W com divided by the compressor efficiency. So in other words, it's 34 divided by compressor work done, which is 6, which is from your example 1.2.4, divided by the efficiency, 70%. So you will write 0.7 and you calculate this out, you should get the answer 4.0. So of course you can write everything in one step, single steps, or you can try to find this first. Okay, you can try to find the power input value first. Okay, you calculate this separately like what I've shown you in the slides. That means you'll find this, which is 8.6 kilowatts. Then finally you take 34 divided by 8.6. So either way. Okay, we will learn two more terms. Okay, these two terms is actually referring back to your pH diagram. Okay, first is degree of superheat. What is degree of superheat? Degree of superheat, it refers to the temperature difference between this point, okay, when it just touches saturated vapor, all the way until T1, okay, the compressor inlet temperature. Okay, because there's a small gap over here, so what is the temperature difference between these two? That is the degree of superheat. So it actually refers to the additional temperature above saturation temperature. So if you are the kind that prefer to use a formula to remember this, so you can actually use a formula. What is the formula? So degree of superheat is in fact equal to T1, which is the compressor inlet temperature, minus away the point where it just touches the saturation vapor line, and that temperature is actually equal to your evaporating temperature. So degree of superheat is T1 minus TE, okay, and it gives you some information because there must be some additional temperature to ensure that all your liquid has converted to vapor. Your compressor cannot take in any liquid, it will damage the compressor. So we have to ensure that. Therefore, you always have to heat up to a certain temperature to make sure that everything has converted to gas. So similarly, for the top part, which is between 0.3, okay, between 0.3 and the saturated liquid, okay, so let's say you have cooled down the refrigerant and it touches this point where it becomes 100% liquid, you continue to cool it down some more, okay, it will reach 0.3. So again, there's some temperature difference over here. So this temperature difference is equal to your degree of subcool. So again, you can use a formula to represent this part. Degree of subcool is actually equal to TC. Okay, TC is the bigger temperature, is the temperature that is higher, that it just come out from the where it just leaves the saturation liquid line, minus T3. Okay, so with that, that's all the formulas that you need to know how to use and what it actually represents.